All right, so here is a final example in class 13, which is a review of things that were covered in dynamics. This is the way that you previously learned. And so here's a 4-bar mechanism as we've come to know them, where we have a input. Let's say this is the crank omega CD of 12 radians per second counterclockwise. The dimensions are 600 right here by BC, which is 400, by CD, which is 350, and the little gap in between here is 200. So based on that, we can get some geometry here. We figure out what the distance is between the ground length and right here between these two, not at least the vertical distance, and then we already have the horizontal distance. And yes, okay. And how do we, yeah, okay. LBC, yep. And then we're also able to figure out what this angle is right up here, right? So we find out the velocity of C. We march through this thing. We find the velocity of C. And then we go to link DC right here. Okay, that's what we just did. Yep. 12 times 0.35 meters per second. And then we can also use this other 3-diagram method for this link right here. And we note that the direction, one of the special things we note is the direction of VB has to be aligned along this axis right here, right, or along this length, along this line. And by the way, this angle right here is going to be the same one as this angle right there. And so for that link, BC, we say the velocity of B, this is the one that we don't know, it's going to be equal to the velocity of C. That's the one that we know. That's the same one as this guy right here, obviously, plus the velocity of B with respect to C. And when done this way, we know that B with respect to C should be to the right. Yeah, so in the x direction, from this diagram up here, this center part, we're going to find that that velocity of B is going to be omega BC times LBC, right? So it's going to be this times this. It's just going to be that horizontal, and that's going to end up being what this is in the x direction. And by the way, we probably could have found that directly right there by writing here instead that VB times the sine of theta was there, so we could have found that right away. But we also know what the vertical component is that has to be in this line right there. And so we could have probably found what the magnitude of VB was right up there. Yes. So we could also come up to link AB right up in here. And by the way, that's because we don't know this yet. That's why we couldn't find it. Okay, so that's why it's kind of like on the back burner. But actually we could have gone no, we were stuck. No, we had to do that. So we go to this other link, right? We put a pin in to this to the center link, and then we find the velocity at B is going to be B with respect to A, right? So we're just this pinned velocity, and we kind of already know the direction that it has to be. Omega has to be clockwise. Is that true? Maybe not. Let me think. Looking at this, yeah, no. This is we have the right directions. Okay, so we find velocity of B right here in the y direction is going to be omega AB times L AB, right, times the cosine, right? So it's going to be, this is the vertical direction right here. So we have this right here, And we know, so we have that, and we know that this, and then we plug numbers in, we know that it has to be this value right here. So we're able to find what omega AB is, right? And we have it like in that direction. So from that, we're able to get the velocity in the x direction. Well, this is, okay, no, that was that was a velocity in the x direction. Yes, we definitely could get that. We could do that in a couple different ways, but we'll get that. And so what we could get is the total velocity. Let's see. We could get the angular. Oh, now we can go back up here, right? So I'm going and I'm using this equation right up here, and I'm finding the angular velocity from that. So now I have the angular velocity of BC as well. And so the velocity of B was something that we were being asked for, and we have the components of it now, right? So we have in the x direction and the y direction, and so that we would find 4.582, and then also we'll find the angle of the thing with the rise over the run is 66.45, which we actually recognize is also 90 degrees minus that 23.56. And if we do the ICR method, we could draw lines that are through the two pinned joints right there. We could see where they connect, and now it's kind of obvious that's what the thing's going to look like, where it's going to rotate about that ICR. And we're able to do that with a little bit of simple geometry. It's not too terribly hard. And we're able to get the same answer. So I'll leave that up there, and you could pause it and walk through and see that we were able to solve these problems, the same problems, with multiple different methods. I think the ICR can be an easy way to do it, as long as the geometry isn't too outrageous. Sometimes it's just a little difficult to work your way through and find it. It's a lot easier when there's a lot of right triangles involved. And when trying to break the geometry down, if it's really tough to try to figure out the lengths of something, I think the best way, or my opinion, the best way, if you're getting stuck on some figuring out these lengths, is to break them down into right triangles and then to add them up into parts. So that's all I have there for that example. You can discard that, and now we're done with a 7-minute video.